Hello, my friend. Welcome to Origins. My name's Don Chapman, and I'm your host. Origins is a forum where we use the evidence of science to validate the truth of creation. We have with us today one of my very favorite guests, Dr. David Minton. For 34 years, he was a professor at the medical school at Washington University. Today, you're going to teach us. Now, we did a previous show. We're talking about the breath of life and how life is in the blood. We did a show on the lungs, we did a show on blood, and now we're going to talk about blood vessels in the heart to kind of complete the cycle. Is that right?
Yep, we need to have the plumbing.
That's right.
We need to have the plumbing to get the blood out there where it's going to do its work, to get out to the big toe and to the liver and the spleen, all the places it has to go.
Some gets to my brain.
And to the brain.
Yeah.
Yeah, we need the plumbing and we need the pump. In a way, we could call the blood vessels the river of life, because they're rather like a river flowing through our body. This is the basic flow diagram. Many years ago, a fellow by the name of Harvey, another Christian by the way, discovered that blood just didn't go out and stay there, but it circulated. It went out and it came back again. So it's a closed loop. We see a kind of a diagram. It's sort of like looking at the subway of Chicago or New York or something. This is the heart. It's right in the center. It's a pump. And blood comes into the heart from the lower part of the body, and it comes into the heart from the upper part of the body, up here.
The blue is the blood coming back.
Right. It's blue because it has lost its oxygen.
Okay.
Blood tends to look red when it has oxygen in it, and it looks blue like venous blood when the oxygen has been expended or used. Okay. And the blood is going to carry primarily nutrients and oxygen, but of course hormones, a lot of other things that are important. From the heart, it gets pumped out to the lungs, so think of this area right here as being the lungs. The blood picks up the oxygen in the lungs, as we mentioned, returns to the left side of the heart, and from there it gets pumped out into the body, where it serves its purpose, to the brain, to the big toe, to the liver, all of the organs. And so this is the general circulatory pattern that we'll be dealing with. The overall picture is something like this. The vessels that go out carrying the oxygen-rich blood we call arteries. The arteries break down into smaller arteries that we call arterioles. The arterioles break down into smaller little vessels yet we call capillaries. These capillaries are tubes that are so narrow that a red blood cell can just fit through one at a time. In other words, you can't get two sideways. They can stack up in rows and go through like a stack of coins, but there's not enough room to go side by side. This is a single file affair that blood can go through the capillaries. To serve its function, oxygen must finally get out of the capillaries, nutrients must get out, hormones have to get out into this area out here in white, where we see the different tissues that need the oxygen, that need the nutrients, that need hormones, etc. So there's a little loop where we leave the capillaries, and then we go into what we call postcapillary venules, and finally back to the vein. So oxygenated blood over here breaks into capillaries, goes back to little venules, to veins, and from veins back to the heart. So some things that get out of the capillaries, of course, return back to the capillaries to go back to the heart again and lung and make another trip through.
There's waste and so forth that has to be carried away.
That's right. You have to take carbon dioxide back to the lung where it can be released from the body, and at the same time pick up new oxygen to take out there. And of course, these capillaries are lining the intestinal tract. So when we eat food, all those nutrients get absorbed into the capillaries there. Yeah. And the liver processes these things. We have little special filters like the spleen that filter the blood. The spleen's wonderful. It takes all those red blood cells and it kind of gives them a beating. It changes the pH and it changes the oxygen tension, and it runs it through a clothes wringer so that it squeezes them just flat. And if the red blood cell can take all of that, then it gets to go one more trip around. So it's sort of like on the train, you got one place that's a gauntlet. And if the cells don't survive the gauntlet, they get taken out of circulation and replaced with new ones. If they do, they get to make it again. A red blood cell lasts about 120 days before it gets pulled out of circulation. This is an interesting photograph where we've actually taken some fatty tissue and we're just looking right through it with the microscope. And what you're seeing here, the blood vessels have been filled with a dye. The dye is red, and so that shows up very well. And you'll notice there's a paired system of blood vessels. There's this thick one, and right next to this little slender line, and when one branches, the other branches, and it pretty much goes through the whole system this way. And now I'll give you a clue. One of these is the artery, carrying the blood out. The other one is the vein, carrying it back. And notice they run together. They don't separate company. They stay side by side. So everywhere the arteries go, the veins go. It surprises a lot of people, but the little narrow one is the artery, carrying the blood out under high pressure, a very fast speed. It's going to go out and branch and branch and branch till you get little tiny things you can hardly see anymore. Do you notice that? Little capillaries out here that are so tiny, they just look like little fringe. The pressure is reduced to almost nothing. The pressure that started in the heart at a high systolic pressure gets reduced to almost nothing, and yet all that blood has to come back again. So how do we get it back? Well, we get it back through the veins. There's no heart out here to pump the blood back. The way the blood gets back is that the veins have to squeeze the blood, and they do so because of the muscles and the tissues around them, and there are valves in those veins, and so the blood is just kind of milked right back to the heart. So it takes a much bigger vessel to get the blood back as far as diameter than to get the blood out, because it's going out fast.
Yeah.
And it's coming back slow. So big channels carrying the blood back, low pressure, slowly. Narrower channels carrying it out. Well, let's go on and look at, this is a section through muscle, like if we took a section right through the skeletal muscle of our arm, and in here we see one of the basic principles of blood vessels, and that is they move in what we call neurovascular bundles. Everywhere an artery goes, a vein goes, and a nerve goes. And they go together, and the reason for that is there's just like a track bed. You know, when you make a railroad track, you have to first of all go out and prepare the track bed. That's where all the expense is. You have to get across all the rivers, you have to get through the swamps and over the mountains and through the tunnels. That's the expense. Once the track bed is there, laying down the rails, no big deal. Same with blood vessels and nerves and veins. They have to follow a track bed, and so once you have that track bed that's built in the embryo, everything follows it. For example, here is an artery, right here, cut in cross-section. You can see blood in the middle. This is muscle in the wall of the artery, so it can adjust its diameter. Next to it, we can use blue because it's a vein. This is a vein, and if you look in the center here, there are valves.
Oh, those are the valves, okay.
Those are the valves. And so when the blood gets squeezed, the valve only allows the blood to go that way. If it tries to come back, the valve closes. So we have valves in the vessels of our legs, and when we move and everything, that blood just gets milked up. That's why if we stand at attention and we don't move a muscle, we can faint because we're not squeezing the blood to get the blood back.
Ah, the movement. You need to move it to move the blood back to the heart.
That's right, because there's no heart out there to pump it back. You got a heart to get it out.
But activity makes those valves work.
But activity's going to bring it back.
Yeah, okay.
And then finally, since you got the roadbed, let's just go right on ahead and put the nerve in there, and here is the nerve. So they run together, and this is true in the big things you can see with the unaided eye, all the way down to what you see in the microscope. Well, this is a comparison of an artery and a vein. The left is an artery, the right is a vein, and I guess the important thing to share with you is all blood vessels are lined with a special layer of cells. These cells are called endothelium. They not only line all the blood vessels down to the capillaries, but they line the heart as well. This lining, whether it's in this vein here or in this artery, is a single layer of little flat cells, like pavement stones.
Right.
And when blood sees those cells, it says, I'm comfortable, I'm at home, all is well.
And as soon as it isn't there, we clot.
But if we go and we make a little tear right here in the wall of that vein, then it'll clot. And that's good, because that's how it plugs a hole, you see. That's the clotting mechanism. Now, outside that endothelium, those special cells, is this layer that looks like Swiss cheese here. And that's elastic tissue. It's like rubber. We have a special biological rubber that is in the walls of our vessels, particularly our arteries. And that means that when the heart pumps, it can stretch a little bit and store some of that energy, and then it can contract. Finally, outside of that is a layer of muscle. Now, the artery has more muscle and more of this elastic tissue than the vein does. This is a photograph of an artery going through the tissue, and we've stained that elastic tissue that's like rubber. We've stained it black, and we see that there is some of this material lining near the endothelium of the artery, and there's another layer outside the muscle. And these two layers work in concert to make the artery nice and stretchy. We'll see this especially when we look at the biggest elastic artery in the body. You know what the biggest artery is. It's the aorta. It's so big you can just about get your thumb in it.
Really?
And its wall, here you're looking at just a section through the wall of the aorta. The blood would be over here, and this is just the wall. And when we look at it there, we see there's a lot of tissue stained red. But if we stain that rubbery material, the elastic tissue in the wall of the artery, if we stain it purple, it's almost one layer of elastic tissue after another. And this is very important because when the heart beats, all of a sudden it's compressing, and there's a sudden burst in pressure. But when the heart isn't beating, when it's relaxing, it goes into what we call diastole, then the pressure is going to drop way down. If our blood vessels are made out of glass or hose like we have for our garden, when the pump hit, the pressure would go sky high, and then when the pump relaxed, the pressure would go almost down to nothing, and then the next time the pump pumped, it would go up high, and we'd have this tremendous range. But the artery, the aorta, has enough of this rubbery material in its wall that it stores that energy by stretching, and then when the heart isn't pumping, it's just contracting to keep the blood going.
All right, well, we're going to talk about the heart as soon as we come back. Don't you go away as we bring in the pump that makes this all work. You'll want to stay with us for that. We'll be right back.
Creation versus evolution. You weigh the evidence. Honeybee technology. What's the buzz about? Honeybees fly with incredible agility that's the envy of stunt pilots. Their navigation software is packed into a brain the size of a sesame seed. Bees have airspeed gauges, gyroscopes, a sophisticated compass, UV sensors to track the horizon, and 2 compound eyes, each with 7,000 sub-eyes. Scientists have yet to design or build anything remotely comparable. Can the honeybee really be a product of random chance processes? Today's guest on Origins, anatomist Dr. David Menton, is a speaker for Answers in Genesis. Audiences enjoy his well-illustrated presentations on a variety of fascinating topics. Many of these lectures are available on DVD. If you're interested in the subject of creation, you'll definitely want these for your own. Orders are being taken at 800-778-3390. You can also write to Answers in Genesis, P.O. Box 510, Hebron, Kentucky 41048, or visit the website at www.answersingenesis.org.
We're back from our break with Dr. David Menton. We've left Dr. Menton up at the board. We're anxious for you to share for us about how the heart works.
Okay, well, let's just take a look at the nature of the problem here. This is a 4-week human embryo, obviously stillborn. It shows that death can come into the world even at this early age. The fingers haven't developed, or the toes, or anything yet. The 2 organs that develop early and become quite large is the brain, which of course we see up here, and the spinal cord, which is growing. In fact, it's growing so fast, the spinal cord is growing beyond the body. And then the heart. We call it the cardiac prominence, and you can see why, because it's huge. That's the heart. This heart needs to be functional right from the beginning. Well, you saw that cardiac prominence, and this is how it works. The heart buds out, and it buds into a sac. You notice this kind of big empty sac, and this little bud is the heart.
Right.
And the heart gets bigger and bigger until it fills that sac. And this space that you see in white is completely eliminated then. Mm-hmm. And left behind is a layer of lubricant. So that when the heart is beating, if it were not for this cardiac sac that's around it, we call it the pericardial sac, the heart would develop friction. One only has to rub the fist against the hand for just a little while and feel how much heat is generated. If we didn't have that lubricated sac, our body core temperature would very, very quickly reach a point that would be fatal.
Wow.
And so something as simple as a lubricated sac around the heart is essential for our very existence.
That's amazing.
I guess when an evolutionist sees something like this, they say, whew, an incredible stroke of dumb luck there that we got that, huh? Well, this is the way the heart looks. If we open up the chest, and the heart resides right here in the center. The lungs are on either side. The lungs are in their sac too.
Right.
And this white, glistening, tough bag is that pericardial sac wrapped around the heart. So we're not looking at the heart, we're looking at the sac that the heart comes in. I think the thing that amazed me most as I began to study the heart is that in a sense we have two hearts.
Oh, really?
We have two pumps. We have the right side of the heart and the left side. We have the right in blue and the left in red. That's as it fits in our body, left here, right here. And the right side is designed to pump the blood that goes to the lungs.
Okay.
And the left side is designed to pump the blood that goes to the body. Now think about this. If the right side sent the blood to the lungs, back to the heart, to the lungs, back to the heart, and the left side sent the blood to the body, back to the heart, to the body, back to the heart, that wouldn't accomplish very much, would it? Because you'd never get the blood to the lungs. When the heart develops, to me this is just mind-boggling. When it develops, there's a spiral that develops in the initial plumbing coming out of the heart that crosses the pipes. And when you have the pipes crisscrossed, as you see them here, look what happens. Blood returns from the body to the right side of the heart. It gets pumped out to the lung over here. From the lung, it goes back to the left side of the heart, not the right, to the left. From the left, it goes out to the body, to the lungs, or to the left side, right side of the heart, out to the lungs, to the left side of the heart, out to the body. You see, it keeps crisscrossing.
It's amazing.
And that crisscross is essential. Sometimes that doesn't develop, that crisscross, and it's called transposition of the great vessels, and it's a very, very serious congenital heart defect for children that have that. It has to be surgically corrected. Well, when we look at the heart, we see there's 4 chambers. On the right side of the heart, we have an upper and lower chamber. This is called the atrium and the ventricle. And the blood comes in from the head and the lower part of the body into the right atrium, goes down through a little trap door. You see this valve here?
Yes, sir.
That valve, the best way to think about it is think of these doors in a kitchen that swing both ways.
Uh-huh.
And it's very important that the doors swing into the big chamber, the ventricle, down, but it can't swing back up again. If it did, when the right side of the heart contracted to send the blood to the lungs, the blood would go right back to where it came from.
You'd never get anywhere.
Right, so this little valve has to open to let the blood in. But when the heart contracts, it has to close. Well, because it's a swinging door, what keeps it from just opening up and sending the blood back up to the atrium? Oh, I'm glad you asked.
I'm glad you're going to tell me.
This is almost too amazing to explain, but these valves that go between the atrium and the ventricle, that are the swinging door type valves, have little strings attached to them. Imagine if on that swinging kitchen door you had little ropes, and the ropes went to the other side of the room. So when the doors swung into the kitchen, that would put slack in the ropes and the air could come in, or the blood in this case. But when the kitchen starts to pump, that chamber pumps, the doors cannot swing out into the anteroom because the ropes stop it. One little problem. when the heart contracts, this chamber gets smaller. That puts slack in these little ropes that hold the valves and would allow the blood to go back into the atrium. But this is prevented by a little muscle whose whole function is to take the slack out of the little ropes that control
What's that muscle called?
the door. That's called a papillary muscle, and you know when you look inside of a heart, it looks like a little man in a parachute, and you got the parachute shroud lines coming down, and that goes to the leaves of the valve.
It's amazing.
So the heart has just some of the most amazing plumbing and valves and what have you that you could imagine. This is what the heart looks like when you take a little piece of it and put it in a microscope. This is a special kind of muscle called cardiac muscle. You see, we have three types of muscle in the body. We have smooth muscle, like in our intestine. We have skeletal muscle, like in our arm. And we have cardiac muscle. And cardiac muscle has a very unusual property, and that is it marches to its own drummer. Every single cardiac muscle cell has the ability to contract in a regular way, just the way your heart does. If you were to remove some of these cells and grow them in a dish, so they were separate heart muscle cells, each of them would sit there and contract to its own signal. But when two of those cells, let's say this is a cell, this is a cell, they might be going like this. As soon as they touch one another, they start working together. So a signal goes from cell to cell to coordinate everything, and the heart is one organ in the body that works without any outside nerve supply. That's why we can transplant hearts.
Yes.
You say, well then, does the heart get a nerve supply? Well, it does. It needs a nerve supply to upregulate and downregulate. That is, to beat faster, you know, when you're exercising, and to beat slower at other times. You would lose that ability if you didn't have nerves coming to the heart. But the heart itself has its own built-in pacemaker so that it contracts steadily on its own. Well, finally, the heart itself has to have blood vessels. We don't think of that, but the wall of the heart is built in such a way that it can't get its nutrition from the blood that's inside of the heart. It needs to have its own vessels, and these are called the coronary vessels. And you've probably heard of coronary bypasses and things like that. Unfortunately, these are vessels that do give problems from time to time. And right here, where the aorta is sending blood out to the body, like this, branching off the aorta, the first two blood vessels to come off the aorta is one going this direction and one going this direction, and they're the left and the right coronary arteries. And they come out and branch and provide blood to the wall of the heart.
To the wall of the heart.
An interesting problem is, can you imagine how much pressure is in that aorta? That heart pumps, and you'd think, why, it would blow these little vessels right out. It would, except for one of the most incredible things. Let me show you how this works. This is just amazing. If you open up that aorta, right where the valve is, starting in the aorta, these are the two openings for those coronary arteries, right there at the beginning.
Okay.
When the heart pumps, the leaflets in the valve of the aorta go up to let the blood go out the aorta. When they go up, they plug the openings to the coronary arteries. See, that goes up and it plugs that hole and that hole. Now when the heart relaxes, you expect the valves to come down again, and then of course the blood pressure, when it's stored in the aorta, could send the blood out into the coronary artery. The problem is that these little valves might stick to the wall of the aorta. But there's a little bulge on these valves that traps blood to keep the valve from sticking to the wall. So when the heart relaxes, that valve can drop down again. Well, I think you can see that the breath of life is extraordinary, and that our heart is not something we think with, as some people think, but it's something that moves the blood.
And it does it in an amazing way. And above all, remember this until you're with us next time. It's God's view that He created you, and that should be your worldview too. Hope to see you again here on Origins. God bless you till then. Dr. Minton, thanks for being with us.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file of program number 811 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins Program, number 811, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.